പൊതുവെ എങ്ങനെയാണെന്ന് അറിഞ്ഞ പോലെ നെറ്റിന്റെ എന്തെങ്കിലും പറയാ. നെറ്റ് ആയതുകൊണ്ടോ യൂട്യൂബിലെ കാണാറുണ്ടോ പൊതുവെ? എന്ത് forming project teams? We'd like you to have found a partner from the class to have... No. എനക്ക് പാർട്ട്ണർ ഒന്നുമില്ല. നമ്മൾ പറഞ്ഞത് ഓർമ്മയില്ലേ, ഞാൻ വേറെ ടീമിൽ. അതാണ് ബെസ്റ്റ്. കാരണം എനക്ക് മോഡൽ ചെക്കിങ്ങും ഉണ്ട്. നീ അവസാനം എന്നോടെല്ലാം ചെയ്യുന്ന എനക്ക് നടക്കില്ല. നീ ആയിരിക്കണം ഇതിൽ പ്രൊജക്ട് ഹൈലി ഫോക്കസ് ചെയ്യുന്നത്.
Someone's mute is unmuted, microphone is unmuted, and there's some crosstalk, so you may want to watch out. Okay, Madhukar.
Yeah, yes, sir.
Yeah, you can start in a minute or so. Yeah,
sure. Yeah, I'll start in a minute.
You have fewer than usual crowd, but nonetheless. Yeah, I think what I want to do is you can go ahead and then start.
Correct.
You know, this discussion. Okay, one thing, if people have already found their teammate to work with, then it's okay. But at the end of your presentation,
yeah,
and after done, so we'll have especially the people that have not yet been able to find their teammate. I request them to hang around if they can, so that we can discuss and then kind of match them with quotes. Okay, so that we'll do at the end. And as I said, today Madhukar will be discussing the paper that I have uploaded. This paper describes one way of constructing an over approximation. We talked about abstraction. I talked about briefly last time. If you construct an over approximation of your actual system, such that the system is also smaller in some respect, then your verification will be easier, because it's the complexity of the system will be reduced, and that you can use to control the complexity of the verification itself. So what Madhukar will be discussing will be this paper, which describes one way of doing this. This paper itself is quite easy to read. So since we are insisting that you should try and use this idea or some idea that of abstracting in your project, I encourage that you should read the paper and make sure that you understand it.
Sir, could you also upload the Hitar's what Hitar showed in about Z3 on Moodle?
Siddharth showed his code as to how he translated it to Z3. Is that the one that you're talking about?
Yeah, exactly.
Okay, I have requested him to upload it. If it is not uploaded yet, I will remind him. Okay. Okay, go ahead, Madhukar. On to you.
Yeah. So the slides, I believe, are visible.
Yes.
Yeah. Yeah. Hi, everyone. So I'll be talking about this paper today. This is what we'll learn this technique that they have proposed for an abstraction-based framework for neural network verification. So of course, from whatever we have seen and learned, we have known that there are ways to specify a network formally. Along with the network, you can also formally specify some precondition, post-condition, and you can try to do formal verification using the help of a solver, let's say Z3. So this is something that we have seen. Of course, we have seen it in a limited context, uh, so it's not clear, whether this technique can always work, whether it works for all kinds of properties or not. But at least we have seen that these things, these neural networks that you learn are verifiable. If you have a property and you can formally state these things, and you can argue about them. There is a way to formally argue about them. So this paper just tries to it's not about it. I mean, it's not. Yeah, so we have not discussed the team stuff. Sahil had a question, and Sahil, we have not discussed.
No, we will be doing that at the end of class. Yeah.
Oh, okay, thanks. Yeah.
So just hang around after Madhukar is done. Okay.
Yeah. Yeah.
I mean, I've requested everyone that has not found a teammate to hang around. People who have already formed their project teams, they found their mate. They could just send us the names of their team.
Yeah. Okay, so this one, yeah. So as I was saying, so this is not primarily about verification, but this is about making the network simpler, so that the task of verification can be done more easily. Okay, and this is what this paper is going to be about. Okay, so a couple of things. First thing, of course, as Sir was saying, that this paper is easy to read. So so it should be possible, in fact, to follow this thing while I am presenting. Except that we need to be a little just a little attentive, because there are some examples that I will go through, and this online or remote thing does not really allow me to point at what I'm showing very nicely. So we may just have to be a little bit alert. But other than that, this does not require any great technical background, or any, even though this is a very recent paper from one of the most premier conferences. It has been stated very, very nicely, and we will be able to follow most of it. So you should try to be with me, and of course ask any questions at any point in time. So I have the chat window on one corner of my screen. So if you post anything on chat, I'll be able to see it immediately also. And you can certainly unmute your mic, and I mean that's also encouraged very much. Okay, so this paper is by these guys. I'm just the presenter here, and okay. Okay, so this is just an introductory slide on what deep neural networks, why are they important. Of course, we are late into this course, so we don't have to worry about why they are important, because we have already seen that they are important. Of course, these are artifacts produced by an ML algorithm. And what the ML algorithm tries to do in general, it tries to generalize a set of examples and into a DNN, and we want to check that, and the beauty of it is that, it is expected to behave correctly on previously unseen inputs. Okay, this is used at a lot of places, and it can be easier to create this than handcrafted software in some cases, and therefore it becomes an effective means to implement complex software systems. So okay, so this is something that we had seen earlier, this airborne collision avoidance system. So this was developed in response to mid-air collisions between commercial aircrafts. And yeah, so the way it used to work was that there was a lookup table. This was of size 2 GB, mapping all the sensor inputs into the output, which was nothing but some advice whether you should turn right or turn left and so on. And this got replaced by a DNN, which is much smaller in size. Of course, the point of saying this is that the DNN is certainly better because it is continuous in nature and it is smaller in size, but it necessitates formal verification, because you cannot just replace the whole lookup table by the DNN. You need to ensure that it satisfies certain properties before you can actually go ahead and replace. Okay. Okay, so what? Yeah. Okay, so this one, yeah. So why are we looking at verification? Of course, once again, these are things that we have seen. So small changes to correctly handle inputs may lead to unexpected and erroneous behavior. Or in other words, we are saying that, look, robustness is a concern in neural networks, right? And testing, of course, it cannot prove in existence of faulty behavior. So therefore, we are interested in verification. So this argument is common, between program verification and neural network verification. So this is a common argument. We cannot rely on testing. Okay. And of course, as we have seen, and this is, there are techniques that can do this task automatically. The task of neural network verification under whatever restrictions or assumptions they may work, but there are techniques that can do this automatically. In fact, it's not too bad. You can verify non-trivial properties about non-trivial networks, and people have done that. And we'll do that ourselves as part of our project, and we'll see how this can be done very efficiently. But in general, it's a hard problem. It becomes exponentially more difficult as the network size increases. And therefore, this paper's contribution is to make the network smaller such that you can continue to check the property that you're checking in the smaller network. Okay. So therefore, we rely on this. So therefore, they propose an abstraction refinement technique, which is what we are going to learn. Okay. So how is this going to work? So what we will do is we will replace the network, the DNN that we have learned, by a smaller abstract network. Okay, and smaller is, in some sense, by smaller I mean that it will become easier to verify. Okay, so in this case it is also syntactically smaller, but what I mean is that it will become easier to verify. Okay. And then we'll of course verify the abstract network. And the way we will do this, the way this abstract network will be constructed, is that if the specification is true on the abstract network, then it will also be true on the original network. Okay. So then we will not have to worry about it. Okay. However, if the specification fails, if the specification is not true on the abstract network, then we will get a counterexample. Okay. And then we will check whether the counterexample is an actual counterexample by simulating the counterexample on the original network. What is the counterexample? The counterexample is basically a set of inputs. Okay, so we'll feed those inputs to the actual network, and we will see whether the output violates the property. Okay, if it does not, that means that it is a spurious counterexample. If it does, then we have already found a set of inputs which violates the property. Okay. So in the case that it is spurious, we will try to refine this network. So we'll try to come up with another network which is a little more accurate than the last abstract network. But by making it a little more accurate, we may also end up making it a little bit larger, or slightly more difficult to verify than the earlier abstract network. the whole thing will still be easier to verify than the original network, but the refinement will, this process of refining will go on, making it more and more accurate and more larger. Slowly, we will reach the original, and the hope is that we will be able to verify the property much before we reach the original size. Okay, so this is what the abstraction refinement story looks like, except that if this refinement is done with the help of your spurious counterexample, then it is, then there are nice things that you can say. You can always say that, look, it's getting better and better. And this is style of using the spuriousness counterexample to refine the abstraction is called counterexample guided abstraction refinement, or CGAR in short. Okay, so the CGAR strategy is a popular one in abstraction refinement. This counterexample guided refinement is a popular strategy. This is regularly used in program verification, and this is something that can be done here also. Okay, and we will see how. Okay, so this is some background which we certainly don't need. So this is what a feed-forward neural network looks like. Of course, the edge weights are missing and the activation function is missing. So for our analysis, we'll assume that we are working with a ReLU activation function. Okay, and how do you evaluate a neuron? You compute the weighted sum and then you apply the activation function, like how we have been seeing. Okay, I've removed the biases. Notice that there are no biases here, and biases, as Hitat was telling us, and we have known that biases do not really make, they do not really add anything in terms of expressiveness or in terms of what you can learn or build. What you can do with biases, you can do without biases also by adding more neurons. Okay, so for simpler analysis, or for simplicity here, we will not talk about biases. So we'll only have edge weights and activation functions. Activation functions will only be ReLU. Edge weights, of course, can be anything, any real number. Okay, this is an example that we have seen very well in the last few lectures. So this is an example of a neural network, and there are some weights, there are some edges, and there's an input layer, output layer, hidden layer. Okay, we have seen this already. Okay, so we come to the question of verification, which also we have seen to some extent. So we have tried to understand what it means to ask this question of verification. Okay, so this question of verification really looks like a triple. Okay, what do we have in the triple? We have the precondition. Okay, we have the post condition, and we have the network. Okay, so these are the three things that we have. For example, if you try to recollect the primality example, you had the precondition that you want to start with an input which is even but not 2. Okay, and the post condition is that the network should not classify it as a prime. Okay, and of course the network is the network that you have learned after training. Okay, or for example, we also looked at ShapeNet network that Hitat had presented. So what was the precondition? The precondition was that in the input example, there should be some cells which are black in color along the edges. Yeah, sorry, just one second. Yeah. So that was the precondition, that there should be some black cells along the edges, or there should be a black square in the center, or some such thing. Okay, and what was the post condition? The post condition was that the network should not classify it as a square, or should classify it as a square, or should not classify it as a cap, and such things, right? And the network, of course, was the network that was trained. Okay. So in general, what does the verification question look like? We ask this question, that is there an input X that satisfies Px and Qy, okay, where Y is the output that you get from by feeding X to the network. Okay, so this is what the verification question looks like, of course. Okay, so in other words, what are we saying? We are saying that, is there an input X such that, the post condition holds. And remember that, the post condition is always the negation of the desired property. Okay, so we want to know, does there exist an input, by passing which to the network, you get an output which is the opposite of the desired property, which is the negation of the desired property. Okay, so this is, of course, we know this, and now we are talking about, this paper. So this paper makes certain assumptions. Okay, so let's look at them. So some of the assumptions are here. I mean, these are all the assumptions that it makes. So it makes an assumption on the network. The network can have only ReLU activation functions, and it can only have a single output node. Okay, which is not very difficult to, I mean, why these assumptions are needed and so on, we are not going to discuss, but these assumptions are easy to understand. Okay, what is the assumption on the precondition? The precondition should just be conjunctions of linear constraints on input values. Okay, so for instance, X has to be less than something, or X has to be equal to something, some such thing. Okay, conjunctions of linear constraints. Okay, and what is the assumption on the post condition? The post condition has the assumption that, it will always be of this form y is greater than c. Remember that, you have a single output node. Okay, so y is the value of the output node. Okay, so the property or the post condition will always be of this form, that y is greater than c for some given constant c. Okay, so you're only going to compare the output with a constant, and you're only going to compare it in this way. Okay, so these are the assumptions. Okay, okay, so on the surface they may seem somewhat limiting, that you can only check very limited kind of properties. It is not actually so. In fact, you can check some interesting properties also, but I'll come back to this towards the end of this talk. Right now, it might be an unwanted digression. Okay, so these are the assumptions that we are going to remember. Okay, oh yes, sorry, I think I have the wrong, wait, sorry, I think I may have the wrong slide. Oh yeah. Yeah, am I audible? About the message. You can see the slides again?
Yeah.
Yeah. Yeah. So at this point, this slide I had pushed to the end, but somehow I had only copied this slide to the end, and it is also. So I thought that I might be using an old deck, which was not good, because I had made many changes later. So I wanted to check that. Yeah. So we'll ignore this slide for now. There's a copy of it in the end, which is when we will look at it. Okay. Okay, so what had we seen? We had seen these assumptions that had been made, and we wanted to say that this is not very limiting, or it is not as limiting as it may seem, but we are going to come back to that. Okay. Okay, so before we go, I just wanted to remind that this verification exercise is something that we have seen. We had these Z3 codes, and we tried to encode this network, this toy network, and you can still find the code for verifying this thing here, and it has some preconditions, post conditions, so you can always revisit this to see how it works. Okay, so now what does this paper suggest? So this paper suggests a technique to do this abstraction. Okay, so what do we mean by this? By this we mean that we will transform the neural network. So we already have this. So remember that we have these three things: the precondition, the post condition, and the network. And right now, what are we doing? We are trying to operate on the network. Okay, so we are trying to transform the network. Okay, so we'll transform this network n into n bar. Okay, how will we do that? We will do that such that the value that n bar computes for any input x is always bigger than or equal to the value that n computes for the same input x. Okay. So we'll try to do this transformation such that this property is preserved during the transformation. So whenever we do this transformation, whenever we make any change to transform this network, we will ensure that, you know, all our changes preserve this property. Okay. Now, what does this give us? This tells us that if the abstract network n bar is safe, which means that, you know, if y is less than equal to c, then the concrete network is also safe. Okay. And notice that, you know, by safe, I have said that, you know, n bar of x is less than equal to c. Because, you know, if you satisfy the post condition, then n bar of x will be greater than c. And post condition is the negation of the desired property. Correct? Okay. So the desired property is actually y is less than equal to c. In other words, it is n bar or whatever, n of x is less than equal to c. Okay. So this is the desired property. Okay. Nothing but the negation of the post condition. There's nothing fancy about this. Okay. Okay. So now, due to this transformation, we know that if the abstract is safe, if we have somehow, after the transformation, we have proved that the abstract satisfies the property, we know that the concrete also satisfies the property. Okay. So this is what we will try to do. This is the sole exercise that we are going to be doing, this transformation. Okay. Okay. Now how will we do this? Okay. So to abstract, we will merge neurons. Okay, and we are going to see all of that. So even if you don't understand, I mean, we should just remember that, you know, we are trying to merge neurons. So we will take two neurons and we will try to merge them into a single neuron. Okay, and what will be our refinement process? We will split them back. So we'll take a merged neuron and we will remove one of the component neurons from the merged one. Okay, this is what we will do. Okay, but we have to wait till we can get there, because right now, you know, this process of merging and splitting cannot be done on this network. So we splitting there. Okay, and I'll slowly take you through all this. Okay, yeah. So are there any questions at this point? I'll just wait 10-15 seconds and take a sip of water.
It looks fine, so you could go on.
Okay. Okay, so we are not, yeah, I was saying, you know, we are not yet doing this this merging and splitting. We are just trying to transform the network into, you know, so this, as you can see in the title, we are taking this network and we are going to transform it into n prime, then to n double prime. And on the n double prime, we will do all our merging and splitting. So right now we are not doing that. Let's just see why, you know, what is this transformation, and then we will worry why this transformation was needed. Okay. So we have this network n, right? So now we want to classify, you know, the hidden neurons in this network. Okay. So one of the things that I want to do is that I want to classify every hidden neuron. So hidden neurons are these, you know, these blue ones. Okay. So I want to classify every hidden neuron as either positive or negative. Okay. So this is what I want to do. Okay. And how will I classify them? So I'll classify them based on the weights of outgoing edges. Okay. So if all the outgoing edges have positive weights, I will say that the neuron is positive, is classified as positive, or is tagged as positive. If all the outgoing edges have negative weights, I will say that the neuron is tagged as negative. Okay, so this is what we want to do. We want to tag a neuron as positive or negative. If all the outgoing edges have positive weights, we will tag it as positive. If all the outgoing edges have negative weights, we will tag it as negative. Okay. Now let's try to see. Okay, so you can see this figure on the left side, you know, the leftmost figure. Okay, so there is this neuron V1 comma 1. Okay, we want to find out whether it is positive or negative. Okay, so we look at the outgoing edges. What are the outgoing edges? There are 3 outgoing edges. Okay, the weights are 2, 1 and -3. Okay, so it cannot be classified as positive or negative because, you know, it's, yeah, because the outgoing edges are both positive and negative. Okay, so now what we will try to do is we will try to split this neuron. Okay, so if you see in the figure in the middle, the second layer, the top 2 neurons. Okay, I don't know if my cursor is visible, but these are the 2 neurons that I'm talking about.
Don't worry, Madhukar. It is quite visible because it shows like a hand.
Yeah,
and it's visible. Don't worry.
yeah. Okay, so these are the 2 neurons that I'm going to talk about. Okay, so what are these? These are V11 plus and V11 minus to denote positive and negative. Okay, and what we have done, so this V11 had 3 outgoing edges and they had positive as well as negative weights. So I have split this. So the weights, the outgoing edges have been split. Okay, so the V11 plus carries all the ones that had positive weights. V11 minus carries all the ones that had negative weights. What happens to the incoming edges? The incoming edges are copied to both the, so whatever was incoming to V11 continues to be incoming to V11 plus as well as to V11 minus with the same weights. Okay, so the incoming edges are copied, the outgoing edges are split into positive on the positive node and the negative ones on the negative node. Okay, so this is what I'm going to do. Okay, so is this part clear? I'll assume that it is clear unless you raise a question. Okay, so yeah, so this is what I did. So I took this network, I took this neuron and I wanted to classify it as positive and negative. It has all kinds of weights in the outgoing edges, so I could not immediately classify it as positive or negative. So what I did, I split them into 2 neurons and then split the outgoing edges across those 2, copied the incoming edges to both, and now I am able to classify them as positive and negative. Okay, and this is what I do. So I do this to all neurons in all hidden layers. Okay, this is something that I systematically do to all hidden neurons in the entire network. Okay, this is what gives me my n prime. Okay, so we have come halfway. We have come from n to n prime. Now we'll try to go from n prime to n double prime. Okay, and after we go to n double prime, we will do our merging and splitting and so on. Okay, so let's see how do we go from n prime to n double prime. Okay, now, okay, so now we have these neurons marked as positive and negative. Okay, so in addition to this marking of positive and negative, we want to mark every neuron as an increment or a decrement neuron. Okay, and what is the idea here? The idea here is that a neuron will be marked as an increment neuron if increasing the value of that neuron increases the output in the end. Okay, it will be marked as a decrement neuron if decreasing the value of that neuron increases the output in the end. The output in the end we always want to increase. Okay, now what should be done to each neuron's value so that the output increases classifies them as increment or decrement. Okay, so let's try to see how this is done. Okay, so this is done by traversing backwards. Okay, now so let's start with the output neuron. Okay, so the output neuron is marked as an increment neuron because increasing the output neuron will increase the output. It's a tautology, it's a useless sentence, but this is what the meaning is, right? So therefore the output neuron gets marked as an increment neuron. Okay, to increase the output, the neuron's value must be increased. Okay, so therefore Y has been marked as an increment neuron. Okay, Okay, so now I'm looking at the figure in the middle. Okay, so now I want to mark the neurons of the layer before Y. Okay, this is done by traversing backwards. Okay, Y has already been marked as an increment neuron. Okay, now what should be the marking for V2, 1 plus? Okay, we want to find out the marking. Remember that, we already have the plus minus markings. Okay, we are already at n prime. So we have done the positive negative marking. Now we are trying to do the increment decrement marking. Okay. So what should be the marking of V2, 1 plus? Okay. So the question that we have to ask is that, if we increase the value of if we increase the value of this neuron V2, 1 plus, will I get more at the output, or will I get lesser at the output? Okay. So since there is an edge of weight 3, or there is a positive weight edge going from there to Y, we know that increasing the value of V2, 1 plus is going to increase the output. Okay. So therefore we mark this as increasing. Okay. The second one, V2, 2 minus. Okay. If we increase the value of this neuron, remember that this value is passed to Y, it is multiplied by the weight of -1, which is the weight of the outgoing edge from this to Y. Okay, so if we increase here, the output decreases. Okay, so therefore we mark this as a decrement node. The third one, V2, 3 plus, is similarly marked as an increment node. Okay, so this is what is happening. Okay, so you had marked Y as increment, and now from a node, if you are coming to Y along, or coming to Y, which is an increment node itself, along a positive edge, you know that has to be marked as increment. If you're coming to Y along a negative edge, then it has to be marked as decrement. Okay. Okay, so this is all that we are trying to do. Okay, so now let's try to do it, for the layer before that also. Okay, so now I'm looking at the figure, which is the rightmost. Okay. Okay, so my layer just before the output layer has been marked as increment and decrement. You can see them as green and pink. Okay, or green and red, however. Okay, so this has been marked as increment and decrement, and now we want to mark V11 plus. Okay, so now what happens to V11 plus? Okay, is V11 plus increment or decrement? Okay, we don't know. Why do we not know? Because V11 plus takes you to both an increment node as well as a decrement node. Okay, so then it becomes difficult to classify that. Okay, so let's split that into two nodes, and let's split the outgoing edges. Okay, which is what has been done. So now you will see two copies of V11 plus on top. These are the two copies of V11 plus on the top. It's exactly the same as before, except that, this 2 and 1 going out of V11 plus has been split into two across these two. Okay. Okay, so what is it that you want to maintain? You want to maintain that, from one node, you don't go to both an increment node as well as a decrement node, because then you will not be able to classify this one, the V11 plus. Okay, so now you have split. Okay, so now things become very easy for you, right? So V21 plus, this node is an increment node. This edge weight is positive. So therefore, this will be an increment node. Okay. Similarly, this is a decrement node. This edge weight is positive. So therefore, this will be a decrement node. Okay. So along positive weight edges, you simply propagate the tagging back. Okay. Along negative weight edges, you change the tagging and then propagate. Okay. So for instance, V23 plus is an increment node. Okay. And here there is an edge weight of -3. Okay. So basically to increase the value here, you must decrease the value here, and therefore, so along a negative weight edge, the tagging gets flipped. Along positive weight edges, you carry on the same tagging. Whether it is positive or negative is immaterial. Along a positive weight edge, you carry on the tagging. Along a negative weight edge, you flip the tagging. Okay. Yeah, so I'll stop here and ask if anyone has any questions.
So here we are doing something more than just checking the derivative of the output with respect to the value of the current node, right?
Oh no, I'm not checking derivative of output or anything. I'm simply doing some manipulation on these edge weights.
Okay.
Okay, so there is
okay.
so there is no derivative or anything here. This is my network. These are the edge weights. Okay. All the learning and all the derivative thing has happened already. Now this is a trained network. You have been given a trained network with neurons and edge weights. Okay, and I'm simply operating on that network.
Correct. So, Diganta, I don't think these are all equivalence preserving transformations. Nothing is, weights are not being changed, and none of the derivatives, nothing. Yeah, none of that is being changed. It's just to get them into a form such that classification is uniformly preserved.
Right.
So this is happening purely on the network. There is nothing else which is there. You know what is there is all visible from here, wherever you're seeing. So you have these network, you have these neurons, you have the edge weights, and now you're trying to what? You're trying to do the same calculation, but you are introducing more intermediate variables. For instance, instead of saying 2 into 3 plus 5 into 7 plus, you are saying now V1 is equal to 2 into 3, V2 is equal to 5 into 7, and it is V1 plus V2. Correct? So it's just that you're introducing more variables, but you're essentially doing the same computation.
Yeah, guys, somebody, there is some crosstalk. So I request that someone whose background is creating that crosstalk mute their microphone. Thank you.
Yeah. Yeah. Okay. So this is what we are trying to do. Okay. So I'll very briefly go over this again. So what are we trying to do? We have this network. We are trying to split. So we are trying to classify them as positive. Every hidden neuron as positive or negative, which is a very simple exercise. If all the outgoing edges are positive, you classify it as positive. If all the outgoing edges are negative, you classify it as negative. If you have outgoing edges which are both positive and negative, then create two copies of the neuron. Preserve the positive weight edges on one, preserve the negative weight edges on one, copy the incoming edges to both, and you are done. Okay. So this is the positive negative thing. Now you're trying to classify them as increment and decrement. The point is that a neuron is increment. If increasing it increases the output, a neuron is decrement. If decreasing its value increases the output. Okay, the output you always want to increase. Okay, so you're asking the question, whether some hidden neurons value must increase or decrease for the output to increase, and that's how you want to classify. So you want to do it by traversing backward. The output neuron is certainly an increment neuron because you want the output to increase. Okay, and now you're trying to go backward. Okay, along a positive weight edge, you propagate the same tagging. Along a negative weight edge, you flip the tagging and propagate. Okay. The only additional thing is that, if some neuron like V11 plus has an outgoing edge to both positive and negative, now you don't know whether, so it has an outgoing edge to both V22 minus, which is a negative, which is a decrement thing, V221 plus, which is an increment thing. And both the edges are 2 and 1. These are both positive edges. So now this one will try to propagate red. This one will try to propagate green, and you don't know what to do. So therefore, you create two copies. You split the outgoing edges such that you only go to increment or you only go to decrement, And now, of course, you are good to propagate again. So you propagate. Okay. So this is what we are trying to do here. Okay. Remember that, it does not change the value computed in the end, because, because you're just trying to do the same computation, except that now you're trying to do it with more neurons. Okay. So it's like saying that, computing the same algebraic expression, but, now you have introduced intermediate variables to capture intermediate expressions or some such thing. It's essentially the same thing. Okay. So now we have done this transformation.
I just
Yeah, sorry.
wanted to make one comment here. Yeah. As a result of this transformation, there's one thing that is not preserved, although they are equivalent. Remember that usually neural networks, the output of every node in a hidden layer is propagated, is connected to every node in the next layer. That thing is not true anymore as a result of this transformation. So, but that's okay. That's not important to preserve the equality. Okay, so the original network had every node in a hidden layer connected to the output going into every other node. That one is no longer preserved as a result of this.
Yeah. Alternatively, you can think of it as preserved, except that the edge weight is 0.
Zero. That is true. Yeah, that's also. So it is as though you have 0.
Yeah.
Okay. Good point. Yeah.
Yeah. Okay. So I'll carry on. Okay. So this is what. Yeah. Okay. So now you have done this part of trying to classify them as positive and increment, negative, decrement, and so on. Okay. So now what is it that you want to do? You want to merge a pair of neurons, and this will be our abstraction thing. Okay, so what is our abstraction? Our abstraction is to take a pair of neurons and merge them. Okay. Now there are constraints under which you can merge. Okay. So you can merge only if these positive, negative attributes and the increment, decrement attributes are the same. And you can only merge in the same layer. You cannot merge neurons across layer. Okay. So you can take two neurons in the same layer which have all the attributes the same. So there are two things, it's either positive or negative or increment or decrement. So if both these things are the same, so it's a positive increment, or a positive decrement. I mean, you can take these kinds of things and you can merge. You can only do so if they are from the same layer. And then you can do it as many times as you want. Okay, because the all the attributes are the same. You can the merged neuron can be thought of as a new neuron with the same attributes. So suppose you're taking a positive increment neuron and merging it with another positive increment neuron. You will obtain a positive increment neuron, and now you can merge that one with a different positive increment neuron, and so on. And you can go on doing this. Okay, you can go on doing this until you have merged everything possible in a layer. Okay. Okay, so if you go on doing it, what will remain? There can at most be 4 neurons remaining in a layer. The positive increment, a positive increment neuron, a positive decrement neuron, a negative increment neuron, and a negative decrement neuron. Okay.
Yeah, you have to define what exactly merging is. Merging neurons also, you have to merge the edges.
Correct. Yeah. So of course, I'll come to that. But the point is that you can take two of them which have the same attribute and you can merge them. Okay. Of course, how you merge them is this, but you can go on doing this. I mean, once you know how to merge, you can go on doing this, and in the end, you will be left with only 4. Okay. If you do this all the way till the end, you will be left with only 4 in each layer, and they will have different attributes. So you can't really merge them. Okay. Okay, so now what does the exact merging process have? Okay, so suppose you're trying to merge two neurons that are both positive and increment. Okay, then what is the merging process exactly? The merging process says that take the max of the incoming edges to those and take the sum of the outgoing edges from those. Okay, so I'll get to an example. Okay, so suppose you're trying to merge V1 and V2. Okay. So if you're trying to merge V1 and V2 from the neuron X1, what are the incoming edges to V1 and V2? There is one to V1 of weight 1.
Hey,
There is
Madhukar,
one. Yeah.
Madhukar,
Yeah.
for some reason, I guess the plus, the pause and neg are labeling is missing. But here everything is pause, I guess. That's why they are.
Correct.
Okay.
Yeah.
So everything is pause here. So you're illustrating for the pause case. Okay.
Correct. All these weights are positive. Notice that 5, 3, 4, they're all positive. Okay.
You're illustrating for the pause ink case.
Yeah. Okay. So what do you do? So what had we tried to say? We had tried to say that takes the max of the incoming and the sum of the outgoing. Okay. So suppose you are trying to merge V1 and V2. Okay. So V1 gets an edge from X1 with weight 1 and V2 gets an edge from X1 with weight 4. Now, if you merge, you cannot get two edges from X1 because these neurons have been merged. You cannot get two edges. Okay. So you have to choose one. Okay. So the strategy says that take the maximum one of the incoming. Okay. So from X1, this merge thing now gets, I'm looking in the middle figures. From X1, the merge thing now gets 4 because 4 is the maximum of 4 comma 1. Okay. And what is the output to y? The output that V2 was giving to y was 3. The output that V1 was giving to y was 5. So now the output that V1 and V2 together gave is 5 plus 3 is equal to 8. Okay. So this is what I mean. Take the max of the incoming and the sum of the outgoing. Okay. So if you want to, let's say, do this again. So suppose you want to merge now this merge node V1, V2 with the third node V3. So suppose now you want to merge these two, right? The merge node and the third node. Okay. So of course, output will become 12, right? 8 plus 4 will become 12, will go to y now, which you can see in the image on the right. Okay. The input will become maximum. So now X1 sends 4 to, I'm just loosely
Wait.
using the word sends 4, but now you know what I mean by sends 4.
Actually, the weight, not the
Correct, not the value. So X1, yeah, so this edge weight is 4 to the merge node, and to V3 the weight is 2. Okay. So therefore X1 will continue to have the maximum of these two edges, which is 4. Okay, so X1 will have this 4 going to V1, V2, V3. Okay. X2 is there is an edge of weight -1 to the merged node, and there is an edge of weight -3 to V3. Okay, so we'll again take the maximum of these two, which is -1, and therefore X2 will have a -1 edge weight to this merged node. Okay, so this is what we are trying to do. We are taking the max of the incoming and the sum of the outgoing. Okay. Of course, as sir had pointed out, we were trying to merge the positive and increment case. Now the same holds for negative and increment case also. So if you have two neurons which are both negative and increment, you again do the same thing. You take the max of their incoming and sum of their outgoing. For the other two cases, you still continue to take the sum of the outgoing, but take the min of the incoming. That's the only thing that changes. Okay. So there are 4 kinds of merging that you can do. For these 2 kinds of merging, you take max of incoming and sum of outgoing. For these 2 kinds of merging, you take min of incoming and sum of outgoing. Okay. Okay. And what is the idea behind this merging? The idea behind this merging is that the new node contributes more to the output than the 2 original nodes. Okay. So this merged node here, V1, V2 merged node, it is contributing more to the output than V1 and V2 were contributing separately together. Okay. So it is, notice that earlier from X1 there was an edge of weight 4 going to V2 and an edge of weight 1 going to V1. Am I audible?
Yeah, you're fine.
Yeah. So from X1, there was an edge of weight 4 going to V2, and there was an edge of weight 1 going to V1. And now you have simply passed the edge of weight 4 to this merge thing. Okay. So this is where you are adding more, you are contributing more. Okay. because to them separately, you would have passed 1 and 4, and you have simply taken max. Okay, so it's like passing 4 and 4 now, not just 1 and 4. Okay. Okay, you can check that this is, this is an abstraction. For instance, here is, at the bottom of this figure, I have written these are basically copied from the paper, but anyway, so so the value of the value computed at the output node is written. R is nothing but ReLU, is the ReLU operator. Okay, so this one, this is the value. When you merge v1 and v2, you are computing this value. When you've merged v1, v2, v3, you are computing this value. Okay, and you can, with some simple arithmetic, you can check that, this the third value is bigger than the second value, which is bigger than the first value. Okay, so this is a simple exercise. Okay, now, yeah, so one of the things which we must notice is this abstraction is independent of the order in which it was done. Okay, so we first merged v1 and v2, and then we merged it with v3. Okay, and to get this, even if we had merged v2 and v3 first, and then we had merged the v2 v3 with v1, we would have still gotten the same thing. Okay, so once you have been given a merged thing, it is independent of the order in which it was done. It will not change. Okay, so no matter how it was done, once all these three are merged, it will be the same thing. Okay. Okay, so for one set of merged things, there is exactly one network that you will get. Okay, so this is what I wanted to say. Okay, are there questions till this point?
How exactly? This does not preserve equality, right?
This,
The merging.
this does not preserve what?
Equality, like the network after
Oh,
merging.
yeah. So the equivalence was only till this stage.
Yeah. So, okay.
Okay, so now we are abstracting it really. Okay, so now, yeah, so if you notice, what had we said? We had said that we will transform the network
Oh,
such
okay.
that,
Yeah.
such that the new network always computes more than the original network for every input. Okay.
Okay.
Okay, this is what we are trying to do, and you can see that the new network computes more. So here are the values that are being computed at the bottom. Okay, and you can see that the merged network always computes more than the.
Yeah, more in the sense large, greater than a real value. Yeah.
Correct. Yeah.
Also, what can we merge any two types of nodes, or like do they have to be the same type, like positive and increasing?
They have to be the same type.
Yeah. Okay.
Okay.
Thank you.
So
Okay.
you only need like an increasing activation function, right? Not necessarily ReLU for this to go ahead.
For this to go ahead, yeah, it has to be a monotonic thing. Yes.
So it has to be monotonic. I mean, as long as it's monotonic, you can still do ReLU satisfying.
Yeah, ReLU is simply because it becomes easier to model and analyze using ReLU than. Okay.
So when we are like actually deciding on how to distribute the weights while we are merging, we're actually ignoring the positive or negative thing, and we're only looking at whether the neurons, whether we are merging are increasing or decreasing, right? So,
you're merging a positive increment with a positive increment, right?
Yeah,
so all the attributes have to be the same.
Yeah, that I get, but like when we are the merging rule, that whether we take the max or the min of the incoming.
Okay, correct. Yeah. The rule is, correct. The rule ignores the positive or negative part.
Right. Yeah.
Correct.
So
The rule is for increment case, you take max of incoming and sum of outgoing. For the decrement case, you take min of incoming and sum of outgoing. That is correct. Yes.
So why exactly, like, what is the motivation behind tracking the positive and negative attributes of these?
See, the positive and negative is tracked because otherwise you will not be able to classify as increment and decrement.
Yeah, so it is actually it's assisting in the process of to determine the classification of ink and dick. Remember that the way that Madhukar described how to go from end, to the output to the thing. The way you were able to classify ink and ink used the pause neg attributes in the process.
Right, and we are only merging pausing with pausing so that So that
Correct,
because
correct.
so that we don't disturb the increment and decrement thing as we do consecutive merges. Right?
Exactly, exactly. So that we don't disturb the increment and decrement thing. Because yeah, what are we trying to preserve? Yeah, the only thing that we are trying to preserve is that the output that is being computed must necessarily be equal or larger. Correct, and this is why we are doing it this way. Is this clear?
Yeah.
Okay. Any other questions? Okay, I assume none, but you can stop me anytime.
Yeah.
Okay. Okay.
No,
So
15 more minutes. Yeah.
yeah.
No,
I'll
but
try
we have
to.
to finish it. Okay, so let's. We started 5 minutes late anyway.
Yeah. Okay. So now, of course, when and as I was saying, you can go on doing this, right? So you can go on doing your abstraction, and then it can become too coarse, right? Because we have merged everything, the entire hidden layer. Now it may have 100, 200 neurons. After you did the transformation, then it potentially it can get multiplied 4 times, because everything you may have to split to classify as positive, negative, and then again split once to classify as increment, decrement. So basically, all these, there can be too many neurons, and by doing this abstraction, you can all merge them into just 4, right? So it can, or I mean, you can choose to stop earlier, but the point is that the abstraction, of course, can become too coarse. Okay. So suppose for x0 the network was computing this, and I mean, this is nothing, this is just a silly example, just trying to motivate the need for refinement. Okay, which need not be done, but I'll anyway go through it. Okay, so suppose for some input, it was computing 3, and now the abstract network is computing 8. Now if this is still fine for the property that you're checking, then it is okay. But if you have abstracted too much, if this 8 is much larger than your property, the property that you're checking, then you need to make it a little bit better. Okay, this is computing you have pushed too much to the output, so now the output has become much larger than the original. Okay, so therefore so you must be aware of the property, and or whatever, so it has to be there is a need for refinement here. Okay, so what does refinement look like? The refinement looks like a different network, n bar prime, such that the value that n bar prime computes is between n and n bar, because n bar was too large. So you want to make it smaller than n bar, but you want to still be bigger than the original n. Okay, which is all pretty standard stuff. Okay, so how do you refine? You pick a neuron,
So
a
here
concrete
you
neuron.
don't mean smaller and larger in terms of the size of the network, but
Oh, this
actually.
is the value computed. Yeah, nx is always the value computed. Okay. Yeah. Okay. So how do we do this? We pick a concrete neuron from the abstract neuron, and then we put it back into the network. Okay. So it's like you operate and remove and put it back. You reestablish that into the network. Okay. Okay, so we'll see examples. Okay, but yeah, but I'll just talk a little bit about the abstraction. So first of all, you can apply abstraction all the way up to saturation to get at most 4 neurons in the hidden layer. I've already explained this. Okay, of course you can control this based on some heuristics. Okay, and the paper talks about a heuristic which they use to control it. I'm not getting into the details because it's not important for this presentation. Secondly, that heuristic did not help them much in their case, but you can read the paper to get this heuristic. Okay, but you can control this. You can control how much you want to abstract. You may have your own heuristics for your own problem, but you can control. You need not go all the way down to 4 neurons. You can choose to stop at some point. I'll do some 10 abstractions and stop, or some 20 and stop, or whatever. You can have some heuristics. Okay, the inaccuracies, as I pointed out, they are being caused by the max and the min operators. Okay, they are causing the inaccuracies. Okay, so what is the general idea? So while merging, we want to merge neurons that approximate the least. Okay, that increase the least. Okay, and while splitting, while refining, we want to restore the one. We want to split the one that restores the most. Okay, this is the general motivation, or this is the general idea. Of course, we'll see what I mean by these things. Okay, so in fact, here is the example. Okay. So this is the heuristic for merging. Okay. So what is the heuristic? It says that, the maximal value of A minus B over all incoming edges with weights A and B has to be the minimal. Okay. So merge such that the maximal value of mod of A minus B over all incoming edges A and B is the minimal. Okay. And let's see this. Okay. Okay. So suppose you decide to merge V1 and V2. Okay. Okay. So you decide to merge V1 and V2. Okay. What are the incoming edge weights, A comma B? So from X1, what is incoming? To V1, 1 is incoming. To V2, 4 is incoming. Okay. So 1 comma 4 is one such AB pair. Okay. From X2, -2 is incoming to V1 and -1 is incoming to V2. Okay. So the other pair is -2, -1. Okay. So you take the max of the differences of A minus B. This is what I had said here. The maximal value of A minus B has to be minimal. Okay. So for if you want to merge V1 and V2, you calculate all these AB pairs, which is nothing but 1 comma 4 from X1 and -2 comma -1 from X2. Okay. Then you take the max of these things. Okay. So max of 1 comma mod of 1 comma 4 and -2 comma -2 minus -1. Okay. So this is 3, this is 1, the max is 3. Okay. So V1 and V2, this maximal value is 3. Similarly for V1 comma V3, if you are merging, so if you are merging V1 comma V3, what is X1 sending to V1? So this is an edge of weight 4. And to V3, it is sending an edge of weight 2. So 1 comma 2. Okay. What is X2 sending? To V1, it is sending -2. To V3, it is sending -3. So -2 comma -3. Okay. So you again compute this max. Okay. Which is 1. Similarly for V2 comma V3, okay, X1 sends 4 to V2 and 2 to V3, so 4 comma 2. Okay, X2 sends -1 to V2 and -3 to V3, so it is -1 comma -3. Okay, so what is the max? This is 2. Okay, so now you take, remember that what are we taking? We are taking the maximal value of this should be minimal. Okay, so which one is the minimum of all these things? 1 is the minimal. Okay, so therefore you merge V1 comma V3 first. Okay, so in this you merge V1 comma V3. Sorry. Okay, this is what we are. Okay, you merge V1 comma V3. And what is the heuristic really saying? It is saying that this new thing should be closest to the ones that are replaced. By any merging, you're going to save a neuron anyway. You're going to remove one neuron from the network anyway. You're going to save one neuron anyway, right? Okay. So by doing this, what are you ensuring? You are ensuring that you don't approximate too much. So you want to merge the one that approximates the least. Okay. This is the merging heuristic. Any questions?
Yeah, one comment that I want to have is this merging first, thing. And so the idea is, rather than saturating it all the way through, if you want to first do partial thing, this is giving you which ones to merge first, so that maybe you could check. And if you're able to check your property with that size, then you don't need to merge any further. Correct? So otherwise, you have to go on doing it. That is the role. That why would you want to decide which ones to merge first? Only if you after each merge you want to check the property. Correct?
Not really. I mean, you may want to merge a few and then check, because with
that is okay. You may want to merge a few. That I understand. But in between, you want to check. Otherwise, if your idea is to saturate anyway, this one doesn't matter.
Correct. Yeah. So how much? Yeah. So how far do you merge is something that you have to develop some heuristics to find out how far do you merge.
You could use whether you can push the verification through or not as the criteria as well. You merge, as few as possible, see if you could verify, you know. If not, then you merge more. Okay, that you can keep
Correct.
doing as well.
Yeah. Correct. Yeah. So what are we? Yeah. So what does this heuristic really say? The heuristic says that look, no matter which two you merge, you are going to reduce the size by one neuron. Okay. So it's okay. So you could merge V1 V2, you could merge V2 V3, you could merge V1 V3. So if we are going to reduce the size, by all three of them, we are going to reduce the size by one. So now let's pick the one which approximates the least, while of course while still reducing the size by one. So by doing this, you're just trying to find out which is the one that approximates the least. Okay, this is what we are going to. Okay, and what does this really say? Intuitively, this says that look, remember what are you doing by merging? While merging, you're changing the edge weight on the incoming edge. You're going to take the max in one case and the min in one case, right? And then you're taking the sum of the outgoing edges. So you are approximating here by taking the max and the min. The inaccuracies, as I was pointing here, the inaccuracies is caused by the max and min operators. Okay, so you're trying to keep the inaccuracies to the least that you can. That's all that you're trying to do. Okay, splitting. Okay, so splitting is another thing. I'll take, yeah. So I already, yeah. So I have like 2 minutes, but it should not take too long. So let me do this.
You have more than that.
Okay, yeah.
You
Okay.
can go to 10 minutes to 5. Okay, 10 minutes. Yeah?
Correct. Yeah. I'll still try to be.
Understand these things as they will be implementing this as part of the project.
Okay. So we need some heuristic for splitting also. How do I decide? So suppose if you're looking at the figure on the right, you have V1, V2, V3 all merged into one. Okay. Now how do you split? How do you know? Should you take V1 out, or should you take V2 out, or should you take V3 out? This is not clear. Okay. So what they suggest is that look, they suggest that it should depend on two factors. Okay, and the factors being this: the edge weight difference between V and V. So V bar is the new neuron which is the merged neuron to which V belongs. Okay, so V bar is nothing but the merged neuron to which V belongs. Okay, so what is the edge weight difference between these two, and what is the difference between the values that are computed for the given counter example? So remember that this was a CGAR thing. Okay, it's a counter example guided thing. Okay, so they say that you consider these two, and I have in the next slide an example of what they mean by consider these two. Okay, so suppose you have a counter example. What does a counter example look like? A counter example is nothing but a valuation to the inputs. Okay, so suppose the counter example is x1 is equal to 1 and x2 is equal to 0. Okay, now what they say is that to decide which one to split, you do the following. Okay, so you first of all you take the original neurons value evaluation. Okay, so what is the value at V1? What does V1 evaluate to for this counter example? X1 is equal to 1 and x2 is equal to 0. What does V1 evaluate to? So of course, if x1 is equal to 1 and x2 is equal to 0, V1 gets 1 into 1 minus 2 into 0. So V1 becomes 1. We know all this. Okay, what does V2 evaluate to? V2 evaluates to 4 into 1 minus 1 into 0, okay, which is 4. What does V3 evaluate to? V3 evaluates to 2 into 1 minus 3 into 0, okay, so which is 2. Okay, so we have calculated the original neurons evaluation. V1 was evaluating to 4, V1 was evaluating to 1, V2 was evaluating to 4, V3 was evaluating to 2. What is the abstract neurons evaluation for the same counter example? So abstract neuron is this. What is its evaluation? So x1, remember that it is 1, x2 is 0. So this becomes 4. 4 times 1. So this becomes 4. Okay. Okay. So one of the things that they say is important is the value difference. Okay, so what is the value difference? So if you have to split v1 out, then the value difference is 4 minus 1, which is 3. If you have to split v2 out, then the value difference is 4 minus 4, which is 0. Okay, if you have to split v3 out, then the value difference is 4 minus 2, which is 2. Okay, so this is the value difference. So this is one of the components. Okay, there is a different thing also. So it should depend on two things. So first of all, by taking this value difference, they are already factoring in this counter example thing. So therefore it is being counter example guided. Okay, the other thing which they say that you should do is you should take the weight difference between v1 and the merged neuron to which v1 belongs. Okay, so what is the weight difference for incoming edges from x1 and x2? Okay, so from x1 the incoming edge to v1 is 1, and from x1 the incoming edge to the merged network, the merged neuron is 4. Okay, so what is the weight difference? 4 minus 1, which is 3. Similarly for x2, what is the weight difference? For x2, the weight going to v1 is minus 2, and here the weight going to the merged network, the merged neuron, is minus 1. So it is minus 2 minus minus 1, which is 1. Okay, and of course we are taking mod of all these things. Okay, so now for every input, or for every neuron in the previous layer, you compute the weight difference like this. Okay, and now they say that remove the vertex for which this product weight difference into value difference is the largest. Okay, okay, so what are the value differences? 3, 0 and 2. Okay, and what are the weight differences? The weight differences is also, yeah, so you can multiply with all these numbers, and you can see that the largest weight difference for v1 is 9, because it's 3 into 3. The value difference is 3, the weight difference is 3. It's also minus 1, but we will take the larger one, so it's 3. Okay, now this one is 0, and this one is 2 into the value difference is also 2, so 2. Okay, so they say that for v1 this value is the biggest, so therefore you should remove v1. Okay, okay, so what did we see? We saw a way to merge, we saw a way to split. Okay, of course this is based on on their intuition. What is the intuition? The intuition is that while merging it should approximate the least, while splitting it should recover the maximum that it can. Okay, are there any questions?
Yeah, one comment I wanted to add was that this anytime, okay, firstly, this because you're adding a new node through the process of refinement, you're always making it more precise, number one. And that is one important to note. So, and the other one is the same counter example will not come back. Okay. So this, by refinement, you will not, you're getting more precise, and therefore you can get a counter example again, but the same counter example will not come back. So you will get it.
Correct. So yeah, so there is a minor thing here. Yeah. So with one refinement, you may not be able to completely eliminate this counter example, but with some number of refinements, you will eventually get rid of this counter example. Yes. So the point is that this is counter example guided. We are factoring in the, what is it that made it worse for this counter example? Which approximation here made it worse for this counter example. So this is also we are trying to factor in by taking this value difference. Okay, so we have the value difference and we have the weight difference, and we take the product of these two because it's dependent on both of these, and we remove the one for which the product is this largest. Okay, so here we remove v1. Okay, so we'll remove v1 from the network. It will continue to have v2 and v3.
So Madhukar,
yeah,
do you have that algorithm picture? So
yeah, it's right here.
Yeah, okay, good. So that gives them the overall view. Okay.
Yeah. Okay. So this is what the algo looks like. Okay. It says that, you can use abstract. Abstract is this operator, which is merging things. Okay. So use abstract to generate an initial over approximation. Then you try to verify. If you are, if you have been able to verify, then you are done. Otherwise, you will extract a counterexample. If the counterexample is actual, when you simulate the counterexample on the original network, if you see that it violates the property, then once again you are done, because it is not a spurious counterexample. It is an actual counterexample. The property does not hold. Okay. Otherwise, the counterexample was spurious, and therefore you need to refine. Okay. And then you refine, from n bar you get n bar prime, and then again, start all over again. Okay. So this goes on, which is what we have been saying. Okay. So you abstract, refine. Whenever you get a counterexample, you check whether it is spurious or not, and then try to use the counterexample like how this said. You can use the counterexample to get your refinement, and then you proceed. So this is typically how any CGAR algo looks like. This is not just about this neural network verification. This is actually the structure of a CGAR algo. Okay, no matter what you're doing, what you're verifying through CGAR, this is the overall structure of a CGAR algo. Okay. I have some 3 more slides, but I'm not sure if there is interest in looking at them, considering we are already past.
No, I think what you should do is, this is anyway a class, so you could let them digest this thing. Okay, and there is also Friday is a holiday, by the way, Gandhi Jayanti. So you'll have some time. I encourage you to go through the paper once with Madhukar's slides and his presentation. So if you have, and you can finish up the 3 things in the next class, okay? The following class before I yeah.
Yeah. Yeah, I'll anyway upload the slides. So there's nothing more in here.
Yes,
you can take a look at this anyway.
But I think this encoding of
Correct.
that don't belong, that's important.
Correct. Yeah. So this is one that I'll take. I don't want to go too much beyond this thing.
Another order of business. So I want to stop here. So, but finish up next time. So yeah. So unless you have questions now, okay? Any questions?
So I'm anyway here. You can ask me questions. I'm here for the next 5 minutes or so. So you can ask me questions. After which sir can end the meeting. I'll upload these slides today itself. I mean, in fact, just right now, I'll try to upload them.
Any questions about Madhukar on this presentation? Okay, so if there are no questions, then I suggest those people who have firmed up any questions about the project guidelines and general questions about project guidelines and so on. Okay, so if there's no question, then the next question is, if you have already firmed up your team, where you can leave, okay? And I request that those people that have not found a teammate to stick around. Okay. Well, if everybody wants to stick around, that means that nobody has found a teammate. Yes, there's no response for anything.
You may want to ask one by one.
What?
You may want to ask one by one.
Ask everyone one by one.
Okay, someone left just now, so maybe.
Okay, I can see. So what? Who all? Okay, let me ask. No. So maybe I'll ask. I'll go through this list of people who are remaining. Anantu.
Yes, sir.
By yes, what do you mean? You're still looking for someone?
Sir, I plan to be with Rishikesh.
You want?
I think I'll be probably grouping up with Rishikesh.
Rishikesh. Is Rishikesh okay with that?
Yeah.
Okay, so then they are okay. So that's good. Argadeep,
Yeah, I haven't found a partner yet.
you haven't found one. Okay.
Yeah.
Diganta,
So I already have planned to partner with Shogat, but
Yogata, huh?
yeah. But yeah. So I wanted to ask you. I think Sahil says that he has already asked you, but I wanted to ask you whether it is possible to make a 3-member team, or is that
No, right now we're not allowing that.
right? Okay. In that case, I mean,
So what
I guess
happens is if I have three, then I have to open that thing up for everyone, and then
yeah. I mean, yeah.
that is number
That
one.
is understandable.
The other thing is then we'll have to adjust the project size so that there
Yes.
is enough for three people to work on and so on.
Right.
Anytime
Yeah.
I found that more than two, it becomes very hard for me to evaluate the project in terms of
Yeah.
contribution. So that's the reason that I'm not in favor of doing that. But you're welcome to work all by yourself if one is willing to do that. Okay. Then also I'll have to somehow adjust. But no, my first preference is that it should be in pairs of two. Now,
Right. Okay.
between the three of you, now you could discuss and then do things. Okay, let me finish up. So I'll assume that you have the partner. So
Yeah.
you have one.
I do. Yeah.
Argadeep does not. Rishikesh does. Kapil and Srijata.
Yes, I am teaming with Kapil.
You are what?
I am teaming with Kapil.
You means who's this? Argadeep.
This is Srijato.
Oh, Srijata. Okay. So Srijata and Kapil are teamed up. So now we
Yeah,
have yeah.
yeah. So we couldn't actually find an interesting paper yet. So do you have
Yeah,
any
that's
suggestions?
the next problem. First, I want to make sure that you have teammates, okay? So that then we know and we can do it. Zubin,
Yeah, I was thinking Sahil.
you have not decided yet?
No, we have we just decided.
Yeah, so we just discussed it in PM. So I guess Zubin and I could partner up.
Okay, so that'll be good. That'll be good in two respects, Sahil. Zubin also has theorem proving background, by the way.
Right, yeah.
Yeah, so that should satisfy your other criteria if you want to come up with some wild ideas, okay? That will include Z3. Of course, it has to be neural network, it has to be Z3, it has to explore abstraction. Anything, any other things that you want to add to the mix to make it more interesting, I'm all for it, okay? So that's good. So there are still a few that are not here, okay? Or maybe everybody is accounted for. No, Diksha is dropped out. There's a couple of people who are not here. Oh, Syed Mukherjee and Diksha, they're not here. So I will send them, I will deal with them separately. At least those people who are here, the things are determined. So I suggest, I request each of you in your team, one of you on each, one of the person on each team, send send us all, Hitarth, Madhukar, and me, a message just confirming that that you two have teamed up. Okay, so that will be like a confirmation message for us, and we'll also keep it on record. If you could do that, I'd appreciate that. Okay. Yeah. Another thing is the second assignment we are working on, writing it up, and it should go sometime this week. And the idea behind that is so it will put you into actually doing some stuff with Z3. Okay. you know, both with DNN and probably with on some general examples as well. So you will get thorough acquaintance with using Z3 on DNN example. Okay.
Sir,
So
in the project, doing abstraction is compulsory.
yes, it is. Yes. So that's why I said that you will have to make the complexity. You see, you will end up doing it anyway, because if it is meets the of anything which is beyond a few tens of nodes, will probably require abstraction. Okay, or I mean, we can discuss. I mean, I would, yeah, I would want you to try doing abstraction, and you will, you know, that's what makes it more interesting. So that. Yeah, because one of
Figure out how to use abstraction in that.
so if you come up with a proposal for another thing, you know, so you surely you can present, discuss with us. Okay. Yes. Yeah, we are within limits. I think it's okay to vary and innovate. Okay, as long as the overall problem is interesting and meets most of our requirements. Okay, if there are no more questions, I will. Anything else you want to add, Madhukar?
It'd be nice to know who else is taking the course, so I can probably ask them.
Who else is taking the course?
Yeah, because not everybody is in here right now.
I guess you don't see the participants list here.
In Moodle you can see it, but there are way more participants than there are actual participants.
Not way more. I mean.
Yeah, in Moodle at least.
Oh, not in Moodle. No. I meant, I'm sorry, the participants here on Zoom. Okay? They are pretty much who are Argadeep Ghosh, Diganta, Rishikesh Balakrishnan, Kapil, Sahil Kulshrestha, Srijata, Zubin. The people who are not here, Anantu, who was here, who left, Sogata, Sayak Mukherjee, who has not been, I mean, maybe he's, at least I've not seen him live on any Zoom sessions. Sayak Mukherjee, Deeksha, I don't know her last name. So those are the people you want to discuss with. But anyway, Kapil, you have teamed up with Argdeep, right?
No, he's Srijata, right?
Oh, Srijata. Argdeep with somebody else. So you wanted to generally discuss things with others, is it? That's why you asked the thing?
No, because I have not found a partner yet, and I don't exactly know many other people taking the courses. So it'd be nice to.
I see. So you. So once again, what's your name?
Argadeep.
Argadeep. Okay. So Argadeep, the Sayak, Deeksha.
Sir, if 3 people are allowed, then we can take him into our team, something like that. If he doesn't find anyone.
Yeah, first I would suggest that you talk to Deeksha and do you know Sayak Mukherjee?
No, I don't. But I mean, I can email them or something. Otherwise, if he attends class, then I can ask him during the Zoom meeting.
Just let me look at the list. Okay, so Deeksha Gopalan, who's not here, so that's a possibility. Anantu said he's already teamed up with somebody, no?
Yeah, Rishikesh.
Rishikesh. Yeah. So Ardeep, you have to the other people that I don't know yet committed is Deeksha, right? Oh, Somadev Mall. Okay. So those are the ones who are not committed yet. So you can speak to any one of them. So Deeksha Gopalan.
Okay.
Mal, MAL, and Sayak Mukherjee. And who else? Must be one more. Algib's the other one, yeah. So
Yeah.
okay. So those are the people that you will have to contact with and see. Yep, you can. I'm sure you can find one. Okay. So I mean, yeah. So first, I want to see if I can all do it in pairs. Yeah. So you have to talk it over with your, partner, and there must be some vibes, that you share. Okay. Make sure of that.
All right, fine. Thank you.
Okay. Thank you. So if there are no further questions, I will end the meeting here. Bye.
Sir, we needed some project ideas.
That we will discuss separately once you found the teammate. Or you have some questions here.
No. I have found my teammate, but I wanted to know some about project ideas.
Yeah. So that we will. Okay. Like I said, we will send a list. Okay. Very soon along with the assignment. So and also if you want to contact one of us and then set up a Zoom meeting, then we can discuss.
Okay.
Stick to the deadline that I've announced. Yeah. So I encourage you to send email to fix up a meeting to discuss. Okay, I'll end the meeting now. Yeah.